All right, so the next thing that we're going to be looking at here is exponential decay. So a common model of exponential growth is your zombie population, as more people get infected, goes up. But the opposite of this would unfortunately be the human population. So if we had humans over the same period of time, we'd start off with a lot, and we would see that humans would go down quite quickly. So this is growth here. Zombies are increasing in number, and the opposite would be humans in the same case. They would be decreasing in number. So exponential decay is what we're going to be looking at. It's actually a very similar model to exponential growth, just a little bit of a different context for how we apply things. So one example is, let's see, we can use how much air is in your lungs, I think, is a model. So you start off with 500 milliliters of air in your lungs, and you replace or you lose 12% of that with each breath. So you obviously replace it, but of that original air that started off in there, you lose 12% every time. And based off of this, we can figure out over how many breaths does it take to basically get rid of or get close to getting rid of all of that air. So in this case, the model that we did above doesn't change. We still have that same starting point. So we're starting off with 500 milliliters of air. The only difference now is what are we multiplying by? So we're losing 12%. So the way that we look at our rate here is if we're losing something, is we have 100% to start with, and whatever we lose, we take away. So in this case, we have 100%, we take 12% away, we're left with 88%. So our rate is going to be 0.88. So it's less than 1. It's going down, and as a result, we're seeing, again, less than 1.88. So let's try this, and let's see if it makes sense. Y equals A times B to the X. Y equals our starting point of 500 milliliters times 0.88. That's what's left, times however many breaths. So after one breath, we could plug in a value of 1, and we would get 440. That seems reasonable, about 12%. So 12% of 500 is 60. So again, going down by that to not 444, I wrote the wrong number. Going to 440 seems to be reasonable after one breath. After two breaths, 0.88, this time squared, times 500, we're left with 387.2 milliliters of air, of the original air, I should say. And let's see, so 500 times 12% that's gone is 60, and then another 12% loss from 440. All right, 440 minus that much, which is a little bit over 50, leads us to that 387 number. Okay, so this function works. So again, you can kind of back your way through this. If you're ever not sure, plug in some numbers, see if what you plugged in is reasonable. But the idea for this is you're basically, whatever you're losing, you're taking that away from the 100% value that you started. So in this case, this function works. Whatever we plug in for x is going to give us an idea of about how much is going down. Another example could be, maybe you're drinking some coffee. You start off with, 200 milligrams of caffeine in your system, and over a certain amount of hours, you lose 20% of the caffeine is lost per hour. So again, you start off with 100% of caffeine, and each hour it goes down by 20%. So here your rate is 0.8 or 80%, and that's also going to be your B value. Your A value is what you started off with, 200 milligrams. So AB to the X power, 200, B is 0.8 to the X power. So again, that would be the caffeine function. You see, because this B value is less than 1, so if the absolute value of B is less than 1, it is decay, or it's going down. You're multiplying by something less than 1. It's a number smaller than 1, so your overall answer is going to become smaller than your starting point every single time. So that's a little bit of the challenge of decay, is really seeing that you're taking it away from 100%. But if you are able to do that and go through with those calculations, you're going to be well set up to interpret these real-world situations. All right, everybody, one more section to go after this. Thanks for listening to our exponential growth and decay model so far. And again, as always, reach out with questions.